In this tutorial, we'll learn how to create a bouncing ball simulation using Webots. We'll start by setting up a simple environment, then add a ball object and apply basic physics properties. Start by adding a circular arena to your Webots world. This will serve as the boundary for the simulation and keep the ball contained as it moves. You can insert the arena from the Webots object library and position it at the center of the scene. Make sure the size is appropriate so there's enough space for the ball to bounce freely. Next, add a directional light to your scene to properly illuminate the arena and the ball. This helps you clearly see the movement and interactions during the simulation. In Webots, you can insert a directional light from the object library and adjust its direction and intensity to get the desired lighting effect. Now, add a base solid node to your scene. This will act as the main physical object that holds properties like mass, translation, and rotation. The solid node is essential for enabling physics interactions in Webots. Place it within the arena and make sure it's properly positioned so other objects, like the ball, can interact with it. Inside the solid node, add a shaped node in the children field. This defines the visual appearance of the object. Within the shape node, add a PBR appearance node to define how the object looks. This allows you to customize properties such as base color, roughness, and metalness. Adjust these values to give your object a realistic or stylized appearance, depending on your preference. Inside the shape node, add a geometry field to define the object's form. For a bouncing ball, use the sphere geometry and adjust its radius to the desired size. This gives the object its physical shape in the simulation. To enable physical interactions, add a bounding object to the solid node. This defines the collision shape of the object. For a ball, you can use a sphere as the bounding object and match its size to the visual geometry. This ensures accurate collision detection when the ball hits the ground or walls. To make your object respond to gravity and collisions, add a physics node to the solid. This allows the ball to move, fall, and bounce naturally in the simulation. You can adjust properties such as mass, density, friction, and restitution bounciness. For a realistic bouncing effect, set a moderate mass and a high restitution value. In the solid node, set the translation field to 0.5. This positions the ball slightly above the arena floor, so it has space to fall and bounce when the simulation starts. The values correspond to the x, y, and z coordinates in the scene, with z being the height. In the solid node, set the center of mass to 0.50. This moves the ball's center of mass slightly above its base, which helps it bounce more naturally and maintain stability during collisions. The values correspond to the x, y, and z coordinates relative to the object's origin. You can update the translation and rotation fields of the ball to any values you like to see how it bounces in different positions or orientations. Changing these values allows you to experiment with different starting heights, angles, and directions, which can make the simulation more dynamic and help you observe how physics affects the motion. You can update the rotation field of the circular arena to see it rotate during the simulation. Adjusting the rotation allows you to experiment with how the ball interacts with a moving or tilted surface, which can make the bouncing behavior more interesting and dynamic. You have successfully learned how to create a bouncing ball simulation in Webots. In this tutorial, you added and configured a circular arena, inserted directional lighting for better visualization, and created a solid object with the shape, appearance, and geometry. You also added a bounding object and physics properties, set the translation, rotation, and center of mass, and experimented with different values to see how the ball bounces and interacts with the arena. With these skills, you can now explore more advanced simulations, add multiple objects, or customize the physics to create more complex and dynamic scenarios.